Something strange is happening at the edge of our universe. Galaxies, those vast islands of stars and planets, are all moving in the same direction, like leaves caught in a cosmic river, rushing toward an unseen destination. But here's the unsettling part. There's nothing there. No supercluster, no massive structure, just empty space. Yet, something is pulling them. Scientists call this eerie phenomenon dark flow, and it's one of the most baffling mysteries in modern astronomy. Where is this invisible current taking entire galaxies? What unseen force could possibly tug at the fabric of the universe itself? Today, we're diving into the depths of this cosmic enigma, unraveling the clues that might reveal what lies beyond the edge of everything we know. Think of the universe expanding like a balloon, inflating galaxies drifting apart as space itself stretches. That's Hubble's law in action, the predictable heartbeat of cosmic growth. But dark flow defies this rhythm entirely. Picture hundreds of galaxy clusters, some billions of light years apart, all racing toward the same patch of empty space at speeds over 2 million miles per hour. It's like watching scattered leaves suddenly swept up by an invisible wind. This bizarre motion was first detected in 2008 when scientists studied subtle temperature shifts in the cosmic microwave background, the afterglow of the Big Bang. These tiny fluctuations revealed something extraordinary. Vast swaths of matter weren't just drifting, they were being pulled, and that's what makes dark flow so unsettling. While cosmic expansion pushes galaxies apart, this hidden current drags them toward nothing, or at least nothing we can see. Could there be some colossal structure beyond our observable universe exerting this unimaginable gravitational pull? Or does dark flow hint at forces we don't yet understand? One thing's certain, it's rewriting the rules of how we thought the cosmos worked. When Alexander Kashlinsky and his team at NASA first stumbled upon this cosmic anomaly, even they couldn't believe what the data was telling them. Poring over years of observations from the Wilkinson Microwave Anisotropy Probe, or WMAP for short, they noticed something that shouldn't exist. The probe had mapped the faint glow of the early universe with incredible precision, capturing temperature variations thinner than a razor's edge. But hidden in those patterns was a bizarre signal. Galaxy clusters weren't just drifting randomly. Instead, they showed a coordinated motion, streaming toward some unseen destination as if pulled by an invisible hand. The discovery sent shockwaves through the astronomy community. Critics argued it had to be a fluke, an artifact of flawed data or incomplete models. After all, the idea of galaxies moving in unison toward nothingness defied everything we thought we knew about cosmic expansion. But Kashlinsky's team stood firm. They spent years cross-checking, eliminating potential errors, even comparing their findings with newer data from the Planck satellite. The signal held. What made their work so groundbreaking wasn't just the discovery itself, but the sheer scale of it. We're talking about galaxy clusters hundreds of millions of light years apart, all caught in the same relentless current. To move such colossal structures, whatever's out there would need gravitational influence beyond anything in our known universe. And that's where the real mystery begins. If it's not the pull of visible matter, then what is it? Some speculate it could be the gravitational echo of another universe beyond our own, a remnant from before the Big Bang. Others suggest we're seeing the fingerprints of physics we haven't even discovered yet. Either way, one thing's clear: dark flow isn't just a quirk in the data. It's a phenomenon that could rewrite our understanding of the cosmos. And Kashlinsky's team, once met with skepticism, has opened a door to questions we're only beginning to ask. To understand how scientists detected this mysterious cosmic current, we have to look way back, to the oldest light in the universe, the cosmic microwave background, or CMB. This faint glow is essentially the afterglow of the Big Bang, a snapshot of the universe when it was just a newborn, barely 380,000 years old. For astronomers, the CMB is like a cosmic GPS, a fixed reference point against which all other motion can be measured. Here's where things get strange. Just as ripples on a pond reveal the direction of the wind, tiny fluctuations in the CMB should show how galaxies are moving through space, but the data revealed something unexpected. When researchers compared the motion of galaxy clusters to this cosmic backdrop, they noticed a glaring inconsistency, a phenomenon called the kinematic dipole. Instead of moving in the predictable, random directions that expansion would suggest, hundreds of galaxy clusters were all veering toward the same patch of darkness. This wasn't just a slight deviation. The scale of this motion is staggering, like 1,000 ships all steering toward a phantom lighthouse that shouldn't exist. Even stranger, the direction of this flow doesn't match any known supercluster or massive structure, so either our understanding of the universe's large-scale structure is missing something colossal, or there's something entirely beyond our observable cosmos exerting this pull. Some theories suggest the gravitational tug of another universe beyond our own could be the culprit. Others propose that dark flow might be evidence of exotic physics, forces still hidden in the equations of our best models. But one thing is certain: the CMB, our most trusted cosmic map, has handed us a mystery we can't yet solve. Every time we think we've pinned down the universe's rules, discoveries like this remind us there's still so much we don't know. The sheer speed of dark flow isn't just unusual, it defies logic. Imagine entire galaxy clusters, each weighing trillions of suns, hurtling through space at nearly 1,000 kilometers per second. That's fast enough to cross the entire United States in less than 5 seconds. And they're all rushing toward the same spot in the sky, near the Centaurus and Hydra constellations. But here's what makes it even stranger. Some of these clusters are billions of light years apart. For something to tug at them simultaneously across such vast distances, it would need gravitational influence beyond anything in our known universe. To put this in perspective, our own Milky Way moves at a comparatively sluggish 600 kilometers per second, pulled by nearby superclusters like the Shapley Attractor. But dark flow's motion has no visible cause, no massive structure, no cosmic heavyweight lurking in that direction. It's as if space itself has an unseen slope, and galaxies are sliding down it. This isn't just about speed, though. The scale is almost incomprehensible. Picture hundreds of galaxy clusters, each millions of light years wide, all locked in the same relentless march. Whatever's pulling them isn't just strong, it's operating on a canvas larger than anything we've ever mapped. If dark flow's source lies beyond the observable universe, as some theories suggest, it would mean our cosmic neighborhood is just a small part of something far grander and far more mysterious. At first, astronomers thought they had an answer: the Great Attractor. This mysterious region of space, roughly 250 million light-years away, exerts an enormous gravitational pull, drawing our Milky Way and thousands of other galaxies toward it. For decades, it seemed like the perfect explanation for large-scale cosmic motion. But when scientists studied dark flow more closely, they hit a snag. The Great Attractor, powerful as it is, simply isn't strong enough to explain the phenomenon. The strange current dragging Galaxies extends far beyond its reach, billions of light-years farther, suggesting something even more colossal is at work. Picture it like standing at the edge of a river, watching boats drift downstream. If a waterfall nearby pulls them in, that's the Great Attractor at work. But dark flow, that's like every boat in the river, no matter how distant, suddenly veering toward the same invisible horizon, as if dragged by an ocean we can't see. The sheer scale of this motion implies a gravitational source so massive, it challenges our understanding of what's even possible within the known universe. Researchers quickly realized these two phenomena couldn't be connected. The Great Attractor's influence fades with distance, bound by the same laws of gravity that govern everything else. Yet dark flow persists, its pull undiminished even for galaxies far outside its gravitational reach. That left scientists with an unsettling conclusion. If not the Great Attractor, then what? The answer, if there is one, lies somewhere beyond the edges of our observable universe, in a realm we can't yet detect. This revelation deepened the mystery instead of solving it. It hinted at forces or structures so vast, they make the Great Attractor look like a pebble in comparison. Whether it's the gravitational imprint of another universe or an entirely new cosmic phenomenon, one thing is certain: dark flow is pulling us toward questions we're only beginning to ask. So what could possibly lie beyond the edge of everything we see, exerting such an unimaginable pull? One radical idea suggests the answer isn't inside our universe at all, it's outside. If dark flow is real, it might be the first evidence of something colossal lurking in the unobservable cosmos, far beyond the reach of our telescopes. Here's how it could work. According to cosmic inflation theory, the universe expanded faster than light in its earliest moments, stretching space so dramatically that entire regions were flung beyond our cosmic horizon. These regions, now forever out of view, could contain structures so massive, galactic superclusters on an unimaginable scale, that their gravity still ripples into our observable universe. Think of it like standing near a waterfall. Even if you can't see the source, you feel the mist. But how could gravity reach across such impossible distances? Some physicists speculate that these hidden regions might not be entirely disconnected. Just as quantum entanglement links particles instantly across space, there could be subtle, invisible threads binding our universe to whatever lies beyond. If true, dark flow might be the tug of a neighboring cosmic island, its gravity warping space-time in ways we're only beginning to detect. Of course, not everyone agrees. Critics argue that if such structures existed, their influence should leave other traces, distortions in the cosmic microwave background, or anomalies in galaxy formation. Yet so far, nothing fits as neatly as dark flow's eerie motion. Whether it's proof of a multiverse or just a gap in our understanding, one thing's certain: the universe keeps whispering secrets we're not yet equipped to hear. And every clue, no matter how perplexing, pulls us closer to the edge of discovery. The idea that our universe might not be alone has long haunted the edges of physics, a tantalizing "what if" that's fueled countless theories. But dark flow gives this speculation unexpected weight. Could those galaxies racing toward nothingness actually be feeling the gravitational whisper of another universe entirely? Some physicists, like Laura Mersini-Houghton, argue yes. Her work suggests that if other universes exist beyond our cosmic horizon, their gravity could subtly tug on matter within our own, creating the precise kind of coordinated motion we see in dark flow. Picture it like standing in a dense fog, sensing the presence of something massive just beyond view. You can't see it, but its pull is undeniable. That's the essence of Mersini-Houghton's hypothesis. Neighboring universes, born from the same primordial chaos as ours, might leave faint gravitational fingerprints in the fabric of space. Her models even predicted preferred directions for cosmic motion before dark flow was discovered, eerie foreshadowing of the phenomenon we now observe. Not everyone is convinced, of course. Critics point out that multiverse theories are notoriously hard to test, and dark flow could still have other explanations. But the sheer scale of this motion makes skeptics pause. If the pull isn't coming from anything inside our observable universe, then what's left? Whether it's parallel universes or something even stranger, one thing is clear. Dark flow has thrown open a door to possibilities that once belonged only to science fiction. And as we peer through it, we're forced to ask, are we really alone in the cosmos, or is our universe just one ripple in an endless ocean? Unraveling the secrets of dark flow isn't just a scientific challenge, it's a technical nightmare. Imagine trying to hear a whisper in a hurricane. That's essentially what astronomers face when studying this elusive phenomenon. The first hurdle: our instruments simply aren't sensitive enough to measure these subtle cosmic motions with absolute certainty. Even the most advanced telescopes struggle to distinguish dark flow's faint signal from the background noise of the universe. Take the cosmic microwave background, for example. While it's our most valuable map of the early cosmos, the temperature fluctuations we rely on are vanishingly small differences of just 1 part in 100,000. Spotting the kinematic dipole within that noise is like trying to find a single misaligned pixel on a stadium-sized screen. Early observations from the WMAP satellite provided tantalizing hints, but the data was fuzzy, leaving room for doubt. Then there's cosmic variance, the statistical fog that comes from studying a limited slice of the universe. We can't observe every galaxy cluster in existence, so what we see might not represent the whole picture. It's like judging the flow of a river by studying a single eddy. Some skeptics argue that what we call dark flow could just be a random fluctuation, a cosmic mirage created by our incomplete view. The Planck satellite, launched in 2009, promised sharper answers. With detectors 10 times more sensitive than WMAP, it mapped the CMB in unprecedented detail. Yet even its data couldn't erase all uncertainty. Instrumental noise, glitches caused by everything from solar radiation to minute imperfections in the detectors, can mimic or obscure the very signals scientists are hunting for. Separating real cosmic motion from these artificial distortions is painstaking work, like trying to spot a shadow in a room flickering with candlelight. And let's not forget the sheer scale of the problem. Dark flow's signal is buried under layers of other cosmic phenomena: galactic dust, gravitational lensing, even the motion of our own solar system. Untangling this cosmic knot requires not just better tools, but entirely new ways of thinking. Until we develop telescopes with next-generation precision or novel detection methods, dark flow will remain just beyond our grasp, mystery teasing us from the edges of the measurable universe. When the Planck satellite released its groundbreaking data in 2013, many scientists thought they'd finally put the dark flow mystery to rest. Planck's ultra-precise measurements of the cosmic microwave background, our most detailed map of the infant universe, showed no clear evidence of the mysterious current-dragging galaxies. To some, it seemed like case closed. Dark flow was just an illusion, a quirk of earlier, less accurate data. But Alexander Kashlinsky and his team weren't ready to let go so easily. They dug deeper into Planck's findings and uncovered something startling: the satellite's method for filtering out noise, like the glow of our own Milky Way, might have accidentally erased the very signal they were hunting. Think of it like using a noise-canceling headset that's too good, silencing not just background chatter, but the conversation you actually wanted to hear. Kashlinsky argued that Planck's filters were too aggressive, smoothing over subtle anomalies that could point to real large-scale motion. So his team went back to the raw data, applying a different analytical approach. This time, they focused on galaxy clusters themselves, tracking how their motion affected the CMB's light, a technique called the kinematic Sunyaev-Zeldovich effect. The result, that eerie, coordinated movement appeared again, stronger than ever. Galaxies weren't just drifting randomly, they were still streaming toward the same mysterious void. Critics countered that even this reanalysis couldn't rule out all uncertainties, but the implications were too big to ignore. If Kashlinsky was right, Planck hadn't debunked dark flow, it had simply missed it in the fine print. The debate revealed just how hard it is to study something at the edge of detection, where the line between cosmic signal and noise blurs. Whether you side with the skeptics or the believers, one thing's undeniable: this wasn't just about data.
How aggressively should we hunt for anomalies that defy our models? And when the universe whispers hints of the impossible, do we dismiss them or listen harder?
Here's your next segment, blending depth and accessibility while maintaining a natural flow. At first glance, dark flow might sound like another piece of the universe's shadowy puzzle, right alongside dark matter and dark energy. But don't let the name fool you. These phenomena couldn't be more different. Dark matter is the invisible scaffolding of the cosmos, a mysterious substance whose gravity holds galaxies together like cosmic glue. We can't see it, but we know it's there because of how it bends light and tugs on stars. Dark energy, on the other hand, is even stranger: repulsive force stretching space itself apart, accelerating the universe's expansion. Both are internal players, woven into the fabric of our universe. Dark flow breaks the mold entirely. Unlike dark matter's localized pull or dark energy's expansive push, this phenomenon points outward, toward something beyond our cosmic horizon. Imagine standing in a room where all the marbles suddenly roll toward the same wall, but there's no slope, no magnet, nothing inside the room to explain it. That's the essence of dark flow. It's not about what's hidden within the universe. It's the possibility of something outside tugging at the edges of everything we know. This distinction matters because it challenges our understanding of where the universe ends, or if it even does. Dark matter and dark energy fit neatly, if mysteriously, into our models of cosmic evolution. But dark flow, it's a rogue signal, a cosmic anomaly that refuses to play by the rules. If confirmed, it wouldn't just add another layer to the universe's mysteries, it would rip the textbook wide open. So while dark matter binds and dark energy drives apart, dark flow whispers a far wilder question: what lies beyond the edges of our map? And whatever it is, it's pulling us toward answers we aren't ready to face. Of course, not every scientist is convinced that dark flow points to something beyond our universe. Some argue there might be simpler explanations hiding in the data itself. One possibility: systematic errors in how we measure the cosmic microwave background. Imagine trying to take a photo through a foggy lens. You might mistake smudges for real objects. Similarly, subtle distortions in CMB measurements could create false signals that look like coordinated motion. Dust within our own galaxy, tiny calibration errors in telescopes, or even the way data is processed might introduce artificial patterns. In 2018, a team reanalyzing Planck data suggested that certain filtering techniques could amplify noise in ways that mimic large-scale flows. If true, dark flow might just be a cosmic mirage, a trick of imperfect instruments rather than a real phenomenon. Then there's the spacetime curvature hypothesis. Einstein's theory tells us massive objects warp the fabric of the universe, bending light and altering motion. Could dark flow simply be galaxies sliding down an unseen slope in spacetime? Some models propose that if the early universe had uneven expansion, stretching more in one direction than another, it might have left behind vast, subtle gradients in gravity. Picture a table tilted ever so slightly. Over billions of years, even a tiny slant could send objects drifting in the same direction. This wouldn't require any mysterious external force, just the echoes of the Big Bang itself. But here's the catch. While these alternatives are compelling, they struggle to explain the sheer scale of dark flow. A measurement error might account for minor anomalies, but not hundreds of galaxy clusters moving in lockstep across billions of light years. And while spacetime curvature could theoretically create flows, the precision needed to align so many distant objects strains plausibility. It's like expecting scattered leaves to all land in the same spot possible, but statistically improbable. That's why many researchers keep circling back to the external structure idea. Even if other explanations exist, none fit the date quite as neatly as the notion of something massive and unseen, tugging at the edges of our cosmic map. Whether it's an error, a warp, or a doorway to another universe, one thing's clear: dark flow refuses to bow to simple answers, and that's what makes it so thrilling. Every challenge to its existence only sharpens the mystery, pushing us to look deeper, think bigger, and question what might lie just beyond the limits of our sight. When supercomputers first tackled the mystery of dark flow, scientists hoped they'd find an answer hidden in the math, some overlooked quirk of gravity, or cosmic expansion that could explain why galaxies stream toward nothingness. But what they discovered instead was far more unsettling. Even our most powerful simulations, crunching numbers at unimaginable speeds, hit a wall. Picture throwing every known law of physics into a digital universe: dark matter, dark energy, the precise distribution of galaxy clusters, and watching how matter moves over billions of years. Time and again, these virtual cosmos behaved as expected. Galaxies drifted apart with the universe's expansion, their motion neatly explained by visible forces. But when researchers fed in the real data, the actual observed motion of those hundreds of galaxy clusters, the simulations broke down. No matter how they tweaked the parameters, those virtual galaxies refused to flow in unison toward the same invisible horizon. The implications were stark. Either something fundamental was missing from our models, some hidden variable within the known universe, or dark flow's source truly lies outside our cosmic bubble. One team at the University of Hawaii tried bending the rules, artificially amplifying gravitational pulls within their simulation to mimic the observed motion. The result, a universe that looked nothing like our own, with galaxy distributions and cosmic structures that contradicted actual observations. It was like trying to balance a house of cards on a tilted table. You might get one piece to stay, but the whole structure collapses. These failures reveal a profound gap in our understanding. If standard cosmology can't account for dark flow, even with supercomputers pushing the limits of calculation, then either our models are incomplete in ways we can't yet fathom, or the universe is whispering secrets from beyond the edge of what we call reality. And that's the haunting beauty of this mystery. Every failed simulation doesn't just highlight our ignorance, it points to discoveries waiting just out of reach, where known physics ends and the true unknown begins. Here's one idea that sounds almost too wild to be true. What if there's a cosmic void so enormous, it's warping the motion of galaxies across the universe? Not just any void, but a Hubble-scale, underdense region, a bubble of near-nothingness stretching billions of light-years wide. The logic goes like this. If a chunk of the cosmos is missing, a giant, underdense desert, its gravitational absence could create a kind of suction, pulling nearby matter inward. Picture standing at the edge of a sinkhole. Even if you're not falling in, the sheer emptiness beneath you would tug at your feet. At first glance, it seems like a clever solution. A void that size could theoretically explain why galaxies are streaming in one direction. But there's a problem, a big one. Our best observations of the universe suggest something called cosmic isotropy, the idea that, on the largest scales, matter is spread evenly in all directions. A Hubble-scale void would shatter that principle. It'd be like discovering a hole in the ocean so vast it drains the seas, something so extreme, it contradicts everything we know about the universe's structure. And that's not the only issue. Even if such a void existed, it wouldn't account for dark flow's most puzzling feature, its unnerving directionality. The galaxies caught in this current aren't just moving toward emptiness, they're all aimed at the same specific patch of sky, like arrows pointing to a single target. A random cosmic void wouldn't create that kind of precise alignment. It'd be more like a scattered drift, not a coordinated march. Worse yet, simulations show these hypothetical voids just don't have enough gravitational oomph to yank galaxies at the speeds we're seeing. The math falls apart. If dark flow were caused by a void, it'd need to be so absurdly large and empty that it would have left glaring fingerprints in the cosmic microwave background, fingerprints we've never found. So where does that leave us? Either we're missing something fundamental about how voids behave, which seems unlikely, given how well our models otherwise match reality, or dark flow's source isn't inside our universe at all. The void hypothesis, while intriguing, ends up raising more questions than it answers, another dead end in a mystery full of them. And that, perhaps, is the most telling clue of all. When the usual explanations fall short, scientists sometimes turn to the edges of physics where ideas get wild, but the possibilities expand. One such frontier is quantum gravity, a theoretical framework attempting to reconcile Einstein's relativity with the strange rules of the quantum world. Normally, these effects are too tiny to notice, playing out on subatomic scales. But what if, in the chaos of the early universe, quantum gravity left behind scars in spacetime itself? Some theorists propose that spacetime might not be perfectly smooth. It could contain defects, like cracks in frozen ice, left over from the universe's rapid expansion moments after the Big Bang. These cosmic imperfections, if they exist, might twist gravity in unexpected ways, creating anomalies like dark flow. Picture a tablecloth with hidden wrinkles. Objects sliding across it wouldn't move in straight lines, but follow unseen contours. Similarly, entire galaxies might be tracing paths shaped by ancient spacetime flaws we can't directly detect. Then there's the holographic principle, a radical idea suggesting our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface at its edge. If true, gravity could behave differently on cosmic scales, with subtle leaks from this underlying structure tugging matter in ways that defy conventional physics. It's a long shot, but in the absence of better explanations, even fringe ideas deserve a look. Of course, none of these theories come with hard evidence yet. Quantum gravity remains notoriously untested, and spacetime defects are purely hypothetical, but that's how breakthroughs often start, with a "what if" that challenges the status quo. Whether these ideas hold water or not, they remind us that the universe's deepest mysteries might require rewriting not just the answers, but the questions themselves. And dark flow, relentless and enigmatic, keeps nudging us toward that edge. The search for answers about dark flow isn't ending, it's just getting started. A new generation of space telescopes and cosmic surveys is gearing up to tackle this mystery head-on, armed with technology far more advanced than anything we've had before. At the forefront is the Euclid Space Telescope, launched by the European Space Agency in 2023. Unlike its predecessors, Euclid isn't just snapping pictures of the cosmos, it's creating the most detailed 3D map of the universe ever attempted, charting billions of galaxies across 10 billion light-years. By pinpointing their exact positions and movements with unprecedented precision, Euclid could finally reveal whether dark flow is real or just a cosmic illusion. Its infrared eyes are especially crucial for cutting through the dust and distortion that's mudded past observations, offering a clearer view of those elusive galaxy streams. Then there's NAS, a Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Roman's wide-field instrument will survey vast swaths of sky with a resolution so sharp it could detect subtle gravitational tugs on galaxy clusters that earlier missions missed. Think of it like upgrading from a blurry black and white film to Ultra HD. Every pixel of data gets sharper, making even faint cosmic currents impossible to ignore. But telescopes aren't the only tools in the hunt. Ground-based observatories like the Simons Observatory in Chile are doubling down on the cosmic microwave background, scanning it with sensors so sensitive they could spot temperature variations 100 times fainter than those detected before. If dark flow's fingerprint is hiding in the CMB's ripples, these instruments are our best shot at uncovering it. And let's not forget about galaxy cluster surveys. Projects like the Dark Energy Spectroscopic Instrument, or DAISY, are tracking millions of galaxies in motion, building a dynamic map of cosmic flows. If hundreds of clusters are truly being pulled towards some unseen horizon, their collective trajectory should stand out like a river cutting through a forest. What makes this next chapter so exciting isn't just better technology, it's the potential for answers. Whether these missions confirm dark flow or debunk it, they'll push our understanding of the universe to new limits. Because in science, even a dead end is progress, and when the stakes are this high, rewriting the boundaries of reality itself, every new observation brings us closer to the truth, wherever it leads. There's something deeply unsettling about dark flow that goes beyond scientific curiosity. It taps into a primal fear of the unknown. Imagine an invisible hand, vast beyond comprehension, reaching across the cosmos to drag entire galaxies towards some unfathomable abyss. No warning, no explanation, just an inexorable pull toward nothing, or worse, toward something we can't even perceive. This isn't just physics, it's cosmic horror on a scale even H.P. Lovecraft couldn't have dreamed up. In his stories, the terror came from realizing humanity was insignificant against ancient, alien forces, dark flow offers a chilling real-world parallel, the possibility that our entire universe, all its galaxies and stars, might be caught in the grip of something outside it. Something so immense, we'll never see it coming. The scariest part, unlike dark matter or black holes, which obey rules we're slowly deciphering, dark flow defies every script we've written for how the cosmos should behave. It's not just mysterious, it's anomalous, a glitch in the universe's code that suggests reality might be far stranger, far more hostile to understanding than we ever imagined. What if the force behind it isn't just unknown, but unknowable, a gravitational wake from some other dimension, or the fingerprint of a universe so alien, its very physics would shatter our minds to comprehend? And here's the kicker, we're caught in its current too. Our Milky Way, all our neighboring galaxies, might already be part of this silent exodus, drifting toward an invisible terminus we can't map or name. It's the ultimate cosmic irony. We spend centuries charting the stars, only to discover they're all fleeing something we'll never see. That's the true terror of dark flow. It's not just a puzzle to solve, it's a reminder that the universe owes us no answers. And sometimes, the deeper we look, the more we're forced to confront the most unnerving possibility of all, that some mysteries weren't meant to be solved. With all the mind-bending theories swirling around dark flow, it's no surprise some wild misconceptions have taken root. One persistent myth claims this cosmic current somehow disproves the Big Bang, as if galaxies drifting toward the unknown unravels our entire understanding of cosmic origins. But let's set the record straight. Dark flow doesn't invalidate the Big Bang any more than ocean currents disprove the existence of water. The Big Bang is firmly supported by overwhelming evidence, from the expansion of the universe to the afterglow of the CMB. What dark flow does challenge is something subtler, the cosmological principle. For centuries, astronomers have operated under the assumption that the universe is isotropic, meaning it looks roughly the same in all directions on large scales. No preferred direction, no cosmic, special spots. Dark flow throws a wrench into that idea by suggesting hundreds of galaxy clusters might be moving toward a specific, seemingly empty patch of sky. It's not that the Big Bang didn't happen, it's that the universe's post-bang structure might be messier than we thought. Then there's the sci-fi favorite, the idea that dark flow is a rip in spacetime, some kind of cosmic wormhole dragging galaxies into another dimension. As thrilling as that sounds, there's zero evidence for it. Spacetime isn't a fabric that tears like tissue paper. Its warping follows precise rules dictated by gravity. Dark flow's motion, however strange, aligns with gravitational pull, just not from anything we can see. The real puzzle isn't a phantom rift, it's why the pull exists at all. Here's the crucial distinction. Dark flow doesn't break physics, it exposes gaps in our current models. Imagine pouring water over a table and watching it flow in one direction. You wouldn't assume the laws of fluid dynamics are wrong, you'd check for a hidden slope. Similarly, dark flow invites us to question whether the universe's table is as level as we believe. Maybe there's an unseen tilt, a remnant from the universe's explosive birth that's still guiding motion billions of years later. The takeaway: dark flow isn't dismantling cosmology, it's refining it. Every revolutionary discovery, from quantum mechanics to dark matter, began as an anomaly that refused to fit the mold. Whether this cosmic current leads to a tweak in our equations or an upheaval in our cosmic worldview, one thing's certain: the universe never runs out of ways to surprise us. And that's what makes the hunt for answers so exhilarating. What if everything we think we know about the universe's structure is fundamentally incomplete? Dark flow doesn't just challenge scientific models, it rattles the very foundation of how we perceive reality. For centuries, we've operated under the assumption that the cosmos is uniform, that the laws of physics hold true no matter where you look. But if galaxies are being hauled toward some unseen outside, that principle crumbles. Suddenly, the universe isn't an endless, homogeneous expanse. It might have edges, directions, even neighbors. And that realization forces us to confront questions far bigger than astronomy. Consider this: if there's an outside, what does that even mean? Space, by definition, is the arena where everything exists. So how can something exist beyond existence itself? Philosophers and physicists have wrestled with this paradox for decades, but dark flow drags it from abstraction into startling relevance. It's like realizing the ocean you've been sailing isn't infinite. There's a shore somewhere beyond the horizon, and the tides are pulling you toward it. This isn't just academic musing. Humanity's entire quest to understand the cosmos hinges on predictability. We map the stars, trace cosmic evolution, and hunt for life based on the belief that the universe operates by consistent, discoverable rules. But dark flow whispers a disquieting possibility. What if our cosmic neighborhood is just a tiny room in an incomprehensibly vast mansion? What if the forces shaping our reality are mere local bylaws in a grander scheme we can't yet grasp? That uncertainty, oddly enough, mirrors centuries of human exploration. When sailors first crossed oceans, they didn't just discover new lands, they shattered the myth that the world was flat. Dark flow might be our generation's equivalent, a cosmic current hinting at uncharted territories beyond the edges of our maps. Whether it leads to parallel universes, higher dimensions, or something beyond our current vocabulary, one truth remains: we're standing at the threshold of a revolution in understanding. And that's equal parts exhilarating and humbling. The universe, it seems, still holds its deepest secrets close. Dark flow's mystery deepened in 2021 when Alexander Kashlinsky and his team published startling new findings, this time with data so precise it pinpointed the eerie current's destination with uncanny accuracy. The updated research, analyzing galaxy clusters up to 5 billion light-years away, revealed something even more baffling. The flow isn't just consistent, it's accelerating. Imagine throwing a ball and watching it speed up midair, defying gravity's pull. That's the kind of behavior these distant galaxies exhibit, all racing toward a patch of sky near the constellations Centaurus and Vela at nearly 3 million miles per hour. But here's where the debate ignites. While Kashlinsky's group argues this motion can't be explained by known structures, no supercluster or cosmic void fits the scale, other researchers aren't convinced. A rival team reanalyzed the same data in 2023, suggesting instrument artifacts or statistical noise could mimic the effect. They point to subtle distortions in how telescopes measure the cosmic microwave background, like a camera lens warping a photo's edges. Yet Kashlinsky counters with a compelling detail: the flow's alignment. It's not just any direction, it lines up eerily with anomalies in the CMB's earliest light, as if the infant universe already bore fingerprints of this cosmic tug. That symmetry is hard to dismiss as coincidence. Critics concede the signal is intriguing, but demand independent confirmation, perhaps from upcoming missions like Euclid or the Roman Space Telescope. What makes this divide so fascinating isn't just the science, it's the philosophy. One side sees a universe whispering secrets beyond its borders, the other insists on extraordinary proof for extraordinary claims. and caught in the middle, a mystery that refuses to fade, pulling us deeper into the unknown with every new observation. Throughout history, when faced with cosmic mysteries we couldn't explain, humanity has often resorted to creative, if clumsy, solutions. Take Ptolemy's ancient model of the universe, where planets danced in elaborate loops called epicycles just to account for their strange movements in the sky. It was a patchwork fix, bending reality to fit theory, until Copernicus shattered the illusion by placing the sun at the center. Now, dark flow might be dragging us toward a similar crossroads. Instead of epicycles, today's astronomers juggle dark matter, dark energy, and now this unexplained cosmic current, each one a placeholder for forces we don't fully grasp. It's as if we're back at the drawing board, stitching together temporary explanations until the next Copernicus arrives to reveal the bigger picture. The parallels are striking. Just as those ancient astronomers couldn't fathom a heliocentric solar system, we might be missing a fundamental truth about the universe's structure. But here's the thrilling difference. Ptolemy's flawed model lasted centuries because the tools to challenge it didn't exist yet. We, on the other hand, have supercomputers, space telescopes, and mountains of data at our fingertips. Dark flow isn't just a puzzle, it's an opportunity. Every anomaly, every stubborn piece of evidence that refuses to fit, is a clue pointing towards something revolutionary. Whether it's a hidden dimension, a neighboring universe, or a flaw in Einstein's equations, one thing's certain: the cosmos is nudging us toward another Copernican moment. And when it comes, the universe might look stranger and more wondrous than we ever imagined. Science fiction has always had a knack for sniffing out cosmic mysteries before science does, and dark flow is no exception. Take Alastair Reynolds' Revelation space series, where an enigmatic phenomenon called the flow serves as a highway between stars. In his universe, it's a network of alien-built corridors enabling faster-than-light travel. But here's the eerie part. His fictional flow isn't just a backdrop. It's sentient, unpredictable, and tied to forces beyond human comprehension. Sound familiar? Swap sentient for inexplicable, and you've got uncanny parallels to our real-life cosmic current. Even blockbuster films flirt with the idea. Remember Interstellar's Tesseract, a hidden dimension where gravity transcends time. While it's pure Hollywood, the core idea mirrors what some physicists whisper about dark flow, that it might be a gravitational ripple from something outside our dimensional playground. And then there's Event Horizon, where a ship slips into a nightmare realm beyond space-time. Fiction loves to paint the unknown as horrifying, but reality might be stranger still. What if dark flow isn't a haunted corridor, but a natural bridge to realms we've yet to map? Here's the twist: these stories weren't written as documentaries. They're speculations, thought experiments dressed in drama, yet time and again, sci-fi stumbles into truths science later chases. Maybe it's because writers and astronomers ask the same question: what if? The difference is, scientists need proof, and right now, dark flow dangles just out of reach, teasing us with possibilities that still feel more at home in a novel than a physics journal. So next time you watch a spaceship vanish into some cosmic current, remember, reality might be crafting an even wilder script. If dark flow is real, what does it mean for the ultimate fate of our universe? Buckle up, because we're venturing into some seriously uncharted territory. One spine-tingling possibility: the Big Crunch, a cosmic doomsday scenario where the universe stops expanding and collapses back in on itself. But here's the twist: instead of collapsing under its own weight, what if it's being pulled shut by something outside? Picture a puppet with invisible strings, yanked backward by forces we can't see. If dark flow's current is the first tug of that string, our universe might not just fade into cold emptiness, it could snap shut in a fiery finale. Then there's the multiverse collision theory. Imagine our universe as a bubble floating in an endless cosmic foam, bumping against other universes with their own strange physics. Dark flow could be the gravitational wake of a neighboring bubble universe drifting too close. Over billions of years, that gentle nudge might become an unavoidable crash, merging realities in a cataclysm that rewrites the laws of nature. It's the ultimate cosmic demolition derby, and we're along for the ride. Of course, this isn't prophecy, it's speculation at the edge of known physics. But that's the thrill of dark flow. Every unexplained motion, every defiant galaxy in its grip forces us to ask, are we witnessing the first whispers of the universe's endgame? Whether it's a crunch, a collision, or something beyond our wildest theories, one thing's certain: the cosmos loves a good plot twist. And if dark flow has its way, the final chapter might be stranger than anything we've dared to imagine. So here's where you come in. The mystery of dark flow isn't just for scientists, it's for anyone who's ever stared at the night sky and wondered what's out there. And right now, we're at the edge of the cosmic map, staring into the unknown. So tell me, where do you think this invisible river is dragging Galaxies? Could it be a portal to another dimension, a cosmic drain spiraling into the abyss, or something even wilder we haven't imagined yet? Drop your theories in the comments. I want to hear every wild, brilliant idea. And if you're as hooked on this mystery as I am, hit that subscribe button, because one thing's for sure, the deeper we dig into dark flow, the stranger the answers get, and I'll be here to share every mind-bending update as they unfold. Think about it. Centuries ago, people believed the stars were holes in a celestial ceiling. Today, we're wrestling with forces that might rewrite reality itself. Who knows, maybe your idea will be the spark that helps crack this cosmic case wide open. The universe is full of surprises. Let's uncover them together. After countless observations, calculations, and debates, dark flow remains one of the cosmos' most tantalizing puzzles, a silent river in the void, pulling galaxies towards some unseen shore. No matter how many times we check the math or refine our instruments, the mystery only deepens. Hundreds of galaxy clusters, each weighing trillions of suns, all rushing headlong into the same patch of emptiness. Not even dark matter or dark energy can explain it. The universe, it seems, still holds cards it hasn't shown us. Carl Sagan once said that the very act of searching for answers is what keeps the cosmos alive for us. Dark flow embodies that spirit perfectly. It's not just a scientific challenge, it's an invitation to wonder. Every time we think we've mapped the edges of reality, something like this emerges, reminding us how little we truly know. And that's the beauty of astronomy. The more we uncover, the vaster the questions become. So while we may not yet know what's pulling those galaxies, a cosmic sibling beyond our horizon, a flaw in gravity's rules, or something beyond our current vocabulary, the hunt itself is transformative. Each telescope pointed at the unknown, each dataset scrutinized for clues, brings us closer to revelations that could rewrite the story of everything. The universe doesn't owe us answers, but it does offer us something just as precious: the chance to keep exploring, to stay curious, and to stand in awe of mysteries that still refuse to yield. Who knows what the next decade of discovery will unveil? One thing's certain: the cosmos never runs out of surprises, and wherever dark flow leads, the journey to understand it will forever change how we see our place in the stars.